Yeah.
Hello, my name is Connie, and I am accompanied with new members of the team.
New member, Marysia, Staton.
Cristian, Teran.
Brian.
And we implement parallel processing on a desktop cluster. So during summer 1, we basically, as you all saw, hopefully, we built the case for the Raspberry Pi cluster out of, in this picture, out of cast acrylic. And I wrote a script to allow the 8 Raspberry Pis to communicate, and we began to plan out phase 2, as you can see in this picture here, by reconnecting all the cables and
So for the goals of summer 2, we are connecting 11 desktop computers together. Well, we have done that already. Right now, we're benchmarking the desktop supercomputers and the Raspberry Pi clusters to compare the performance. So we're going to run scripts and benchmarks on all 11 desktops, and then do some type of calculation, as well as with the Raspberry Pi cluster, to see which is faster, processing-wise. And then we're going to investigate how the desktop cluster can be scaled up. So we're trying to go up as far as maybe 20 plus computers to see if that would work together and how fast the 20 plus computers can be. So we did come across some problems and challenges during this the research. The first problem we had was brownout. There was a thunderstorm, and the power just went out for a few seconds in the building, which completely wiped everything on the computers. So we had to start over. We went to each desktop to configure and allow the booting process to boot from the external hard drives that we had plugged into the computers, all 11 desktops. So we went to each one by one, went into the BIOS system, reconfigured, and we then installed and then reinstalled a succession of Linux distros into the external hard drives.
So at that point, they started coming across a few different issues with the distribution that they had installed, something called Mint, which isn't really meant to do anything with high performance computing. So we did a little bit of research, and we found out that there's a distribution called Pelican HPC, and that one's made specifically for you to cluster computers pretty easily if you know what you're doing. All right, it can take as less like 5 minutes, 6 minutes, something to do like that. But as we were testing, we found out that the secure shell wasn't really working. The permission keys were not syncing up. We really couldn't figure it out why. But then, in a stroke of brilliance, we decided to downgrade from 4.1 to 3.1, and it just started working. Everything started working together. Everybody started talking to each other, and then, we started actually doing benchmark testings, and just ran a few scripts to see how fast everything was really going. And then I'm just going to give you a little bit more about what Pelican HPC is.
So Pelican HPC is based on Debian, which is a pretty old established version of Linux, and it's by default a live build. It is also not permanent, so has to be made permanent, and it allows us to perform parallel computing using MPI. MPI stands for Message Passing Interface. And as my co-host mentioned before, about Linux Mint, and it's not made for clusters, it's missing compilers, and Pelican HPC is specifically made for clusters, as mentioned before.
Alright, so then once we started using Pelican 3.1, we finally got the desktop to start talking to each other, as Brian said, and this is the first benchmark that happened that is integrated to the Pelican system. So we can see that it's recognizing all the 11 desktops, and it has a calculation time of 0.34 seconds, and the speed of the cluster is 5,000 megaflops, which stands for mega floating point operations per second, which is operations, arithmetic operations using decimals, which is the measurement unit for performance speed of clusters.
So with that, like if you have a simple calculation, 8 plus 5, you can add that up, no problem. But if you have something 123.46 minus 27.5, it requires a lot of thinking. That's where the floating comes into play.
So in this graph, it basically describes that the succession of number of processors. So every time we add a processor, the computing time decreases, which makes sense because it's calculating things faster. And however, this is a little bit slower because we implemented MPI run, which is what Vinny said before, and it makes it slower. It has a slower performance rate.
So going from there, as the graph showed, the current challenges are that the performance of the cluster starts stagnating or showing plateaus after using 4 nodes. So going from 4 nodes onwards, it doesn't show any improvement. So our hypothesis is that the program that we're testing on the cluster may be too small or too simple for it to show the improvement of using several nodes at a time. So it's taking more effort into communicating between the nodes than actually solving the problem. So to solve this, we're going to try to use a more complex benchmark, figuring out how to actually understand the results we're getting, to completely understand it, and to run some C++ code files to see how it performs with that.
OpenMPI allows it to communicate with each other, allows the computers to communicate with each other, so you can use OpenMPI. NPD is a file extension, you need OpenMPI to run.
Okay, so our current tasks are to, we basically installed LinTech Supercomputer Benchmark, which is the most recent benchmark to basically test very high performance clusters. And we're currently investigating some simple C++ code files that are commonly used to test parallel performance because most of us know how to use C++, or else, and then MPI 4Pi is basically already built into Pelican HPC, but Brian is the only one that knows Python in this group. So we're basically we're trying to find C++ code files. And okay, so InfiniBand, so our current switch is very slow. Like it's been here for a while, and InfiniBand Internet Connect is very expensive. However, it basically has switches like up to 1 gigabit per second, so it's pretty fast. And we're trying to, however, we can't really do that because it's too expensive.
Too expensive. And Cesar?
Thank you.